Okay, so let's solve this problem like we are in an interview. So the problem is scalar multiplication of a matrix. Write a Python function that multiplies a matrix by scalar and returns the result. So we are given a 2D matrix and a scalar. So and a scalar number that's just one value, not a like vector or matrix. And basically our job is to multiply every single element inside this matrix by scalar and return a matrix of the exact same shape. So the shape of the matrix will remain the same because we are multiplying by scalar. Yeah, and so we have a 2D matrix. Let's call the size as m comma n, and then we have a scalar. Let's call it as a c. Just basically this is just one number and we need to produce so the output is tensor, right? It's not a list. That's what we need to mention to the interviewer as well. And we need to produce an output tensor where basically every position I comma j in the matrix has a value multiplied by c times, right? And so, and this is just a linear operation, so it will preserve the shape. And just giving you a little background, so generally these are used in like Adam optimizers when we scale moments, and these are the metrics like these scalar multiplication we do either to scale in attention, like when we do 1 by root dk, and even in dropout, like technically like when we invert dropout multiplies by 1 by 1 minus p. So it's kind of a building block of every problem. And so the first, like some of the important tips that we should do for to is like, as I told, like ask that confirm the return type. So here return type is tensor, and torch dot tensor, and then like what data type should we assume for the input. So the input, since here there is no data type, so it would be a good question to ask the interviewer. And for now, like we can consider, just since we are using PyTorch, so we'll just consider it as a float, mostly like float 32. And this matters because integer multiplications can overflow, and generally like float 32 is standard in deep learning. Now, so one more thing can we ask, like is this input a matrix? Can it be a Python list of lists? It can be a NumPy array or a torch dot tensor. So mostly like here the expected answer is, since we don't have any data type, so the expected answer they would say is that all three. So okay, and what else we need? So one more thing is that can the scalar be a Python int or Python floor or a zero-dimensional tensor? And should we also handle like negative scalars and zeros, because scalars can be anything. So like the expected answer that the interviewer will say, mostly any numerical scalar is fine, like negative and zeros multiply by 0 will give a 0 matrix, and multiply by negative 1 negates everything. So yeah, mostly like we need to handle this case. Now we'll start telling the law. This will be mostly questions. So logic. So the logic is mostly like straightforward. We take the input matrix and we convert it into a PyTorch tensor. So and then we can start like just multiplying the tensor with a scalar. So yeah. So let's implement the code once we are like once you and interviewer both agree we'll start implementing the code. So first thing is that this already is done. So basically we have already a float tensor and the input is already converted to the tensor, so we don't need to worry about here. And basically the result will be, so we'll be doing element wise multiplication. So in PyTorch the shape of tensor is like, as I told, m comma n, and then we multiply the scalar of shape. So broadcasting spans the scalar into like every element without allocating like an extra n tensor full of the scalar value. So basically this directly implements like c into a of ij for all ij, and then so we'll assign a new variable and then we'll just multiply m tensor into a scalar, and then we'll at the end return the result, and the result will be a tensor. So the code is very simple, but I want to explain like how even with the simple problems, the problems that how would we approach in the interview, and we have to actually mention like how the shape is preserved. So here what's happening is that element wise multiplication. So here when we multiply a tensor with a scalar, it's mostly element wise multiplication using broadcasting. So a tensor of shape m comma n and scalar of like scalar. So what does broadcasting do is it expands the scalar across every element without allocating an m comma and tensor full of the scalar value. So also it's very important concept because it is vectorized on CPU or GPU. So this directly implements like b of ij equals to c into a of whatever ij. So for all of ij, and yeah, and we assign it to a new variable result. So this basically holds the final output tensor b of the same shape as empty, because we are now it's just a multiplications, and then we return the, so we could write here that shape is preserved, and yeah. So this should be the first thing. They might ask like, why are you using like torch dot as tensor? So because torch dot as tensor will copy the data if the input is in the Python list. So we have Python list of lists, it will copy the data, or if even the d type needs to change, and this is kind of a hidden allocation, so we cannot fully avoid this as for list of lists. But like if the tensors are, as we said, like if the tensors are already in a float of 32, like this will create, this can be just like we could just do empty dot multiply or mul scalar. So yeah, that would be one optimizations, but then again we have to like check if it is an instance like of the metric, like because we have to check that if the matrix of d dot like data type of matrix is torch dot float 32 or not. If it is, if like it is float 32, then we can reuse this, and otherwise like it's just a simple problem, so will not go. And And yeah, so what we could do is we could run over some of the edge cases, like let's suppose the edge case is this or this. So here, like torch dot edge tensor produces a 1D array, so tensor is of shape 0, so multiplication will still work uh, and will return an empty tensor. And the other case would be like, let's suppose if we have 5, so the shape is here 1 comma 1, and because so what we are doing is that we are multiplying tensor of 1 comma 1 will still return a tensor of 1 comma 1. The second edge case would be like when scalar is 0, so if you multiply 0 it will give a 0, and even with like negative ones, so suppose if you multiply 1 comma 2 and then 3 comma 4 with minus 1, it will still be like multiplied and everything will become minus 1 minus 2 with so yeah. And we could even like trace through these examples, like and in tensor it will mostly be like, since we are dealing with tensors, it will be because float 32 tensors, so shape will still be same and then will multiply. So firstly, like the logic is again the same, equals to c into a of iz. So firstly it will get like 0 comma 0, so 0 comma 0 is here 2, so into 1 is still, it will still be 2, and then similarly b of 0 comma 1 will be 2 in 0 comma 1 will be 2 into 2, so it will become 4, and b of 1 comma 0 will become 2 into 3, so 6, and then b of 1 comma 1 is to 2 into 4, and make sure to write it is a capital B because it's a name of the matrix, so it will be 8. So result will be a kind of a tensor of 2 dot 4 dot comma 6 and 8 dot. So as you can see, the shape is still preserved, so shape will be 2 comma 2. So one more thing is that for this example, like nothing would break, but if matrix is like 1e to the power 20 or 2e20 and scalar is also very big, then float 32, every element would become infinity, because float 32 max value is approximately 3.4 E38, I guess. So then it will overflow, and we need to do float 64, so that is one thing we could do. And generally, like other thing that you could discuss about, like production considerations. So in production systems, generally this exact like operations should be fused with the surroundings operations, mostly using JIT compilers like torch dot compile or like